Unit 9, Molecular Geometry, pages 207 and 214, Vesper Theory. We'll start with electron domains. They are regions of space occupied by electrons. In reality, the electrons are located in molecular orbitals that can be bonding or non-bonding. So this Lewis structure has one domain here, a second domain here, and the lone pair makes a third domain at the top. So there are three total domains around this nitrogen atom. Single, double, and triple bonds each count as one domain, and any lone pair is also one domain. The central nitrogen atom has three electron domains. The multiple bond counts as one domain because both bonds occupy the same region of space. The single bond is domain number 2, and the non-bonding electron pair, sometimes called the lone pair, is domain 3. The Vesper model. Why is CO2 linear while NO2 negative is bent? So here, CO2 has two electron domains, 1, 2, about the central carbon atom, while NO3 has three domains, 1, 2, 3. Electron domains will repel each other. So two domains avoid each other by assuming a linear geometry, which is 180 degrees from one another, is the farthest that they can be from each other due to repulsions. The three domains have to avoid each other by assuming a planar geometry with 120 degree angles between the domains. This is why NO2 is considered bent. Bent because if I ignore the lone pair, the two other domains that are bonded domains end up in a bent configuration as opposed to a straight across linear configuration. So the Vesper model stands for the valence shell electron pair repulsion model, which predicts that the optimum geometry of a molecule is established by minimizing the repulsions of the electron domains on the central atom. NO2 negative assumes a bent geometry to minimize repulsions between the lone pair of electrons on the nitrogen and the two bonding electrons domains. Okay, you need to understand the difference between an electron domain geometry and a molecular geometry. The electron domain geometry, or just domain geometry, describes the geometry of all the electron domains about the central atom. The left diagram shows all of the electrons. There are three domains, 1, 2, 3, and the geometry about the central atom is called Trigonal Planar because there are three total domains. The molecular geometry is going to be the shape of the molecule when you ignore the lone pair of electrons. In other words, imagine the lone pair, which is here, but we've taken it off in order to focus on the molecular geometry, the geometry of all the atoms, not including the lone pair on the central. So the molecular geometry describes the geometry of the atoms only. The diagram on the right shows the atoms. The non-bonding electrons help determine this geometry but are invisible in the picture on the right. To determine the molecular geometry, pretend the non-bonding electrons are invisible. Use your thumb to cover up the non-bonding electrons on the central atom and determine the geometry. So the molecular geometry just based on these guys is going to be considered bent. So NO2 negative has a resonance hybrid. The actual NO2 negative molecule does not contain one NO single bond and one N double bonded to O, as shown in this Lewis structure here. The real molecule is a mixture of these two resonance structures. As shown in the model below, both bonds in the actual molecule are identical. They have the same bond length and the same bond association enthalpy. Each bond is about 1.5 bonds in strength. The geometry is bent because of the repulsions of the lone pair electrons predicted by the Vesper model. So there is still the lone pair up here at the top. They're just not being, they're ignored, and so we have a bent structure with the rest of the atoms. Predicting geometries for Lewis structures. To find the geometry of a molecule predicted from Vesper theory, you have to draw the Lewis structure first. Then count the electron domains around the central atom in the Lewis structure. Identify the number of bonding and non-bonding domains around the central atom. Look up the geometry in the table, and then examples of each type of molecular geometry are on the next few pages. All of these geometries are derived by finding the best way for the electron domains to avoid each other and minimize their electron-electron repulsions. So here is the table on page 212, and for this course you're going to have to actually memorize all the different possible molecular geometries as well as their bond angles. They can be described as the total number of domains. So you'll notice that when there are two domains, there's only one possible geometry, and that's going to be linear. When you have three domains, there's two possible geometries, which are going to be trigonal planar and bent. When you have four domains, there's three possible geometries. 5 domains has 4 possible geometries, and then we have only 3 that we have of interest when you have 6 domains. So a better way to visualize these is with the chart on the next few pages, where the structures are actually drawn out. And so if you have only 2 domains, then it's going to be linear with a 180-degree bond angle. If you have 3 domains, then there's 2 possibilities. Here, you have 3 bonded atoms, or you have 2 bonded atoms with 1 lone pair. So this one is called trigonal planar because it's flat in the plane and it makes a triangle when you connect the 3 atoms. This one is considered bent because when I ignore the lone pairs, my atoms here make a bent configuration as opposed to a linear. If I have 4 domains, then there are 3 possible drawings. If you have 4 bonded atoms, you're going to have what's called a tetrahedral. The bond angles here are going to be 109.5 degrees, and that's going to be equal between all atoms. So 109.5 here, 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 and under there. If you have 1 lone pair at the top and 3 bonded atoms, you have a total of 4 domains still, but the molecular geometry, ignoring the lone pair, is called Trigonal Pyramidal. Notice you have a triangular. So if I connect these at the base, you have a pyramid that has a triangular base. And then down here, if I have 2 lone pairs and 2 bonded atoms, ignoring the 2 lone pairs gives us the bent configuration again. So if you have a lone pair present, then the bond angles are actually pushed slightly closer to one another down here. So you're actually looking at a little less than 109.5. And because this has 2 lone pairs, then the bond angle here is actually less than 109.5 because they're pushed even closer together for the 2 lone pairs of electrons. Back up to 3 domains, it's 120 degrees between all 3 of these hydrogens. However, because this has a lone pair, the bond angle here is going to be less than 120 degrees. 5 domains is called Trigonal Bi-Pyramidal. So here you have 1, 2, 3, 4, 5 domains. What you want to look at it as, if I ignore these 3, notice you have 2 atoms that are totally vertical, like 180 degrees from each other. And these are called axial positions, the straight up and straight down. And now imagine these 3 are actually around the center rotating, if you would. So these are flat, and they are in a 120 degree angle from each other, while each of these 3 are 90 degrees from the axial position atoms. These are called equatorial and these are called axial. So if you have 1 lone pair, so if one of these 5 is a lone pair, let's ignore that and you're going to get something called seesaw. And I invite you to look at this and notice here's a seat, here are the 2 legs to the seesaw. If you have 2 lone pairs, that's this one here, and you ignore the 2 lone pairs, notice you have a T-shaped molecule. And then over here, we have 3 lone pairs, and so notice if you ignore those, then you have a linear molecule. The axial positions are the only ones that are counted. Finally, here's 6 domains, and we only care about 3 of their potential structures. Here you have your 1, 2, 3, 4, 5, 6 total domains. Again, we have 2 vertical axial positions, and then we have a flat cross here making our square in the middle. If we have 1 lone pair at the bottom, then notice that we have what's called square pyramidal. We have a pyramid if you connect these to each other, and then on the base of the pyramid we have 1, 2, 3, 4, that these form a square, and then this makes the pyramid. If you have 2 lone pairs, then you'll notice that we can ignore the axial positions, and now we just have the flat cross in the middle. That's going to be called square planar. Planar means flat in the plane. You're going to be asked to memorize all geometry names and shapes. Here is your note card for this section. Electron domain geometry. Each of the following count as 1 domain: a single bond, a double bond, a triple bond, or a lone pair on the central atom. each are one domain. If you have two total domains around the center atom, then you have a linear electron domain geometry. 3 domains is called Trigonal Planar, 4 domains Tetrahedral, 5 domains Trigonal Bi-Pyramidal, and 6 domains is Octahedral. The molecular geometry is going to be the shape of the molecule when the lone pairs are ignored.